These are the notes for AP Calculus on the topic of polar functions without the graphing calculator continued. So here it says in polar coordinates the curve C, so the name of this curve C, shown below is given by r equals 5 over 3 plus sine theta. So there's our polar function there. And you can see the interval it applies on is from 0 to 2 pi, which is the most common interval you'll see, but you can also see other intervals on these polar ones. And then it says find dr d theta. So notice not dy dx, which would be the slope of the tangent, the actual dr d theta. So the derivative of this one. And then we'll look at the other one. Let's find that first. All right, so you could take the derivative right now using the quotient rule, and that'd be fine. However, it might be a little simpler because the numerator is just a constant. If you rewrite this as r equals 5, and then bring the 3 plus sine theta up to the numerator, and then it's to the -1 power. And then you no longer need the quotient rule, you just need the power and chain rule. So now when you find the derivative, since the variables are r and theta, it would be dr d theta equals, bring down the -1 times 5, it's -5. And then function side stays the same, 3 plus sine theta. Subtract 1 from the exponent, so the -2. But then we've got this function inside, so you've got to use the chain rule and multiply by the derivative of the function inside. And the derivative of 3 is 0, plus the derivative of sine is cosine. And then let's go ahead and simplify this, because we'll need to work with it in the next thing it asks for. So dr d theta. Well, on the numerator, we'll have this -5 times cosine theta. And then on the denominator, we move this down there with a negative exponent. Now it will become 3 plus the sine of theta squared. So that's the first thing it asks for in part A. We found dr d theta. And it says as theta increases, in other words, as it goes from 0 and then all the way up to 2 pi, what intervals is the distance between the origin and the point r theta increase? So if we've got some point on our graph, really put it anywhere, let's say we put it right here, say that's the point r theta. Then the distance between that and the origin, we draw a line there. Well, notice that distance here, really, that's what r itself represents, how far it is from the origin. Theta is the angle, and r is, in polar coordinates, how far it is from the origin. So this whole expression, the distance between the origin and the point r theta, is really another way of saying r. So we want to know when is r and what interval is increasing. So we're using the same techniques we use for regular rectangular coordinates, just with polar coordinates. So we found the derivative, and then to find the critical numbers, before we draw an interval line, see what makes the derivative 0 or undefined. So to see what makes it 0, you'd set the numerator equal to 0. Let's see, -5 will never be 0, but cosine theta could equal 0. So where's cosine equal to 0? You can draw our unit circle there between 0 and 2 pi. Well, cosine is the x-coordinate. So the x-coordinate is 0 right here at the point 0, 1. That's the angle pi over 2. So that's one critical number. And also right down here, that's the point 0, -1 at 3 pi over 2. So those would be two critical numbers. Theta equals pi over 2, and theta equals 3 pi over 2. Both of those make the derivative equal to 0. And you would also, to see critical numbers can also make the derivative undefined. So when you have a fraction like this, you want to see what makes the denominator 0. So don't worry about the square right now. If what's inside the 3 plus sine theta is equal to 0, squaring 0 will still keep it 0. So we really just set 3 plus sine theta equal to 0. And then if you solve this to isolate the sine, you'd subtract the 3. So you get sine theta equals negative 3. But there's a couple ways to see this is not going to work. One is, remember the graph of sine goes to the origin, fluctuates back and forth like this. It really just goes back and forth between the values of -1 and +1. So there's no way sine will ever equal -3 unless like the amplitude was 3 or larger, which is not in this case. So that's one way to see there's no solution. Another way is if you try to draw a triangle here on a unit circle, sine is the opposite over hypotenuse. So you have to make the opposite -3, the hypotenuse 1. So the opposite would have to be longer than the hypotenuse, which is an impossible triangle. So that's another way to see this doesn't actually ever equal -3. So we don't get any critical numbers this time for the denominator, just the ones for the numerator, pi over 2 and 3 pi over 2. Then we can draw our number line. Our interval is from 0 to 2 pi. And we've got pi over 2 and 3 pi over 2. And label it with our first derivative, which is dr d theta. And both pi over 2 and 3 pi over 2 make the numerator 0, so those make the derivative 0. If there were any that came from the denominator, those would be undefined. And then we can just start testing there. And the first interval, since 0 is not a critical number, we could test 0. And notice a shortcut here in your derivative. Since the denominator is squared, the denominator will never be negative, so we really just have to focus on the numerator. And substitute in here cosine, but then notice it gets multiplied by -5. So cosine of 0, we plug in 0. Cosine right here at 0 is 1 times -5, it's negative. Here you could test pi. Cosine of pi is -1 times -5 makes it positive. And here you could test 2 pi, but that's really the same as testing 0 here. So it's still going to be +1 times -5 gives you negative. So this shows us that the original function r, which is what we're trying to find, is increasing or decreasing. When the derivative is negative, r will be decreasing, then increasing, and then decreasing. You can see in this case it asks for the increasing intervals. In this case there's only one. So we can say, and I'll just use the same wording they used here, even though this does mean r, just to make sure it's clear that we're answering the question they asked. And say the distance between the origin and the point r theta is increasing on, interval would be from pi over 2 to 3 pi over 2. And then it says give a reason for your answer, just so it's saying justify. So the reason why we know that it's increasing on that interval is since dr d theta, our derivative, is positive, or you could say is greater than 0, on, you could write on this interval, or you could just list interval since there's only one. Might be easier to do that. All right, let's take a look at the next one here, which is part B. So we have the same overall polar equation here. So now we're asked, it says let S, we've got some region S here, be the region inside curve C, but outside the curve R equals 2. So again, here's curve C right here, which they already graphed for you. And outside the curve R equals 2. Well, in polar coordinates, notice in this one there's no theta. The radius is always 2, which means the angle doesn't matter. So whenever the radius is a constant like this, that's just going to produce a circle with a radius equal to 2. So no matter what angle it is, R is always 2 basically. Whenever you have R equals a constant like that. So you can see these polar coordinates always start at the origin here, so 0, 2 this way, 2 this way, 2 this way, and 2 this way, and you can draw, best you can, just a circle through those 4 points. That'd be perfect there. See, mine's definitely not. Try to draw this part a little bit better here. And so region S is the region inside curve C, so this is R equals 2 right here. And this one is curve C right here. So it's inside our original curve C, but it's outside our circle. So you can see outside the circle, but inside C, that would be talking about this region right here. That's region S that it's talking about. And it says write but do not evaluate, so we're just setting this one up. An integral expression for the area of S. So notice this area, sometimes we just have one polar curve, but this one is in between two polar curves. In which case we've got to use the formula here that kind of looks like the disk method, although it's not the same because it's area, not volume. But it's really this one right here. It goes between two polar graphs. Still have the 1/2 out in front, the starting angle and the stopping angle. But you have the outer radius, R1 squared, minus the inner radius, R2 squared. And the outer radius is the one that's farther from the origin, the inner radius is the one closer to the origin. So let's figure out if we can see if we can find R1 and R2 for this graph. Okay. So R1, again, on polar coordinates, the radii always start at the origin. So R1 in this region is the one further away, which you can see is curve C. So R1 is 5/3 plus sine theta. And R2 is the inner radius, the one we're going to subtract. So to right there, R2, which is our circle. So R2 is just equal to 2. And then we're just setting this one up. So on the outside we've got 1/2. But then notice when we start to write the integral, we need to know the starting and stopping angles, which you can see it starts and stops right where the points intersect. So to find where they intersect, you can just solve this by using substitution, substituting the 2 directly in for R. So we'd have 2 equals 5/3 plus sine theta. And then you can either cross multiply 2/1 or multiply both sides by 3 plus sine theta, which are easier to think about. So if we cross multiply and multiply this side by 2, we get 2 times 3 is 6 plus 2 times sine theta would equal 5 times 1. And then to solve this, first isolate the sign by subtracting 6. Both sides. So we get 2 sine theta equals -1. And then dividing by 2. So we're looking for where sine theta is equal to -1/2. So let's draw that on our unit circle there. Think about what quadrant is sine negative. Well, remember, sine is the opposite over the hypotenuse. So the opposite has to be negative. And where the opposite is negative is in quadrants 3 and 4. So we can draw that in there. opposite -1 right here, hypotenuse 2, opposite -1, hypotenuse 2. You can see that's our 30, 60, 90 triangle. And this is 30 degrees, which is pi over 6. So this is pi, which is 6 pi over 6, plus pi over 6 gives you 7 pi over 6. And this one is pi over 6 less than 12 pi over 6, which is 2 pi over 6. So 12 pi over 6 minus pi over 6, this one's 11 pi over 6. And then you can see if that matches up with the graph. You can see, oh yeah, 7 pi over 6 is in this direction. It can either go this way, or if r was negative, it can go the opposite way, but that's it. So you can see this one, it looks reasonable for 7 pi over 6. And this one looks reasonable for 11 pi over 6. Right? So you can kind of see if the answers you get here make sense based on where the points of intersection look like that. So we can go from 7 pi over 6 to 11 pi over 6. And then the whole thing is going to be times d theta. And then we have r1, or outer radius squared. 5/3 plus sine of theta squared minus inner radius is 2 squared. Or you could just simplify that to 2 squared to just be 4. That'd be fine as well. You could also square this out as 25 and then the denominator squared. But again, we're just writing but not evaluating, so there's no need to simplify it even beyond this. So this is the integral that would give us the area of region S right here. It's between the two polar graphs. All right, let's take a look at a couple more here. The next one says a polar curve is given by the equation r equals 8 theta divided by theta squared plus 1 for theta greater than or equal to 0. So we just have basically no negative angles here. And then it asks, this is our polar equation, what is the instantaneous rate of change of r with respect to theta? Let's first look at that expression. Well, rate of change is another word for the derivative. And it tells you what the derivative notation should be here. When it says r with respect to theta, that means dr, and then with respect to, that's the one that's on the denominator derivative, d theta. So that's what we're looking for, equals question mark. And the reason why it's instantaneous, the r d theta would give you the derivative at any angle, but instantaneous, when you're looking at one specific angle, in this case, when theta equals 2. So it might look a little weird having that angle that's not, doesn't have pi with it. But remember, radians are just numbers. They're just often written with pi, but they don't have to be. So we're looking for dr d theta specifically when theta is 2. All right, so here, unlike the first one we went over, I wouldn't recommend trying to avoid the quotient rule, because if you move this up to the numerator, you're just going to end up having to use the product rule and the chain rule. So it's probably easier in this case to just use the quotient rule. And that's because both the numerator and denominator have variables. Neither one's a constant. On that first problem, remember the numerator was a constant, which is why it was easier to rewrite it, so we didn't have to use quotient rule. So let's find dr d theta using the quotient rule. So you'd have to derive the numerator. Might look a little weird with a theta in there, but derivative rules work the same way as theta as they do for x or t or any other variable. The derivative of 8 theta, just like the derivative of 8x, would just be 8 times the denominator, theta squared plus 1 as it is, minus the numerator as it is, which is 8 theta, times the derivative of the denominator, which is 2 theta, all divided by the denominator squared. And you could substitute in 2 right now, but it might be a little easier if we simplify this first. So here, if we distribute out the 8, we'll get 8 theta squared plus 8, and then multiply these together gives you negative 16 theta squared. And the denominator, though, I'd probably just leave like this. It's probably easier if we don't square it out. Simpler in this factor formula. And then you can combine the like terms. The 8 theta squared minus 16 theta squared is negative 8 theta squared. So we have 8 minus 8 theta squared divided by theta squared plus 1 squared. So there's our simplified derivative. You can even factor out the 8 here and factor, but we're not trying to find the critical numbers like we did on the first one to find increasing and decreasing intervals, so there's no need to do that. It's probably easier to just substitute in the theta equals 2 right now. So now dRd theta, specifically when theta equals 2, would be 8 minus 8 times 2 squared divided by 2 squared plus 1 squared. And that'll give you on the numerator 8 minus 2 squared is 4 times 8, so 8 minus 32. Over 2 squared plus 1, that's 5 squared. 8 minus 32 gives you negative 24. Over 5 squared is 25. In this case, that doesn't reduce at all. Sometimes it might. I know. Let's take a look at one more. And this one combines something you learned earlier with these Riemann sums with these polar coordinates. So a little different on this one though. It says let R be the region bounded by the graph of the polar curve R equals f of theta, and the lines theta equals 0 and theta equals 1 as shaded in the figure above. So when you have angles, theta equals a constant. Remember when it was the R equals a constant, that created a circle with a constant radius. Well, when angle is a constant, theta equals 0 is this direction. And now, since there's no R, that means the radius can be anything. So it creates this horizontal line right there on the x-axis. So this is just the x-axis, basically. And theta equals 1. Well, pi over 2, that's like 3.14 approximately, divided by 2 is a little more than 1 as a radian. And so the radian is 1 is going to be here in the first quadrant. Notice again, it's just linear. So you're always going to get these linear equations when theta is equal to a constant, as opposed to when R is equal to a constant, you get a circle for these polar coordinates. Because again, this means the angle is 1, but R can be anything. And then the table above gives values of the polar function R equals f of theta. So elected values of theta tells you what R is equal to. Okay, so we don't have the actual equation, we just have it as selected values. And what's the approximation for the area of region R using a left Riemann sum with 4 equal subintervals? So, since they're equal subintervals, remember what you can do first is to get the width of them. To get the width of the whole interval, well, let's first write down, it would be easier if we write down our expression that we're approximating to see the width of the whole thing. So, a little different on this one. With area, it's a little simpler. With rectangular parts, you just integrate the function and that's it. You get the area in the curve. But here, with polar coordinates, you have to have the 1/2 out in front. And in this case, notice it starts at theta equals 0, that's our starting angle. And stops at theta equals 1, there's our stopping angle from 0 to 1. And it's not just case it's called f of theta. I'll call it r of theta in general squared. Or you could write f of theta squared, either way. F is just a specific function we're given. So the width overall comes from the lower and upper limits, so the 1 minus 0 of the interval, and then divided by the number of subintervals. We're told is 4. So we can see the width in this case is 1/4. So that's the width of each subinterval. So now we can draw our number line here, going by 1/4. So it'd be 0, 1/4, 2/4, which is the same as 1/2, 3/4, and then 4/4, which is the same as 1. There's our 4 equal subintervals. And we're using a left Riemann sum. So when we're approximating this, we still have the 1/2 out in front. And then times, to approximate this integral, we'll have, what's different here is we're going to have r of theta squared. So we have the width is 1/4. And then r of theta, well, the left endpoint on the first subinterval from 0 to 1/4 is at 0. So 1/4 r of 0 squared plus 1/4. The left endpoint on 1/4 to 1/2 is 1/4. R of 1/4 squared plus the left endpoint on 1/2 to 3/4 is 1/2. So 1/4 r of 1/2 squared plus 1/4. The last one, the last left endpoint, from 3/4 to 1 on that subinterval is a 3/4. So r of 3/4 squared. And again, this whole thing is times the 1/2 out in front from our area formula for polar graphs. Okay, so that's a setup similar to rectangle, just a little more complicated because of the square there and the 1/2 out in front. And then to simplify our calculations, notice since they have equal widths, you can factor the 1/4 out of all the terms times the 1/2 out in front. Will give you 1/8. And then we just have to have each of these squared. And that's where our table comes into play. So r of 0 is 2. So we'll have 2 squared plus r of 1/4 is 8. So 8 squared plus r of 1/4, sorry, r of 1/2 is the next one, is 6 squared plus r of 3/4 is 10 squared. And then we've got that 1/8 times the whole thing. So we just keep simplifying this. We've got 1/8 2 squared is 4 plus 8 squared, 64. Plus 6 squared, 36. Plus 10 squared, 100. I've got 1/8 times, well, let's see, 64 plus 36, notice that's 100, plus another 100 is 200, plus the 4, 204. And 8 doesn't go into 204, but we can reduce that and divide them both by 4. That gives you 8 divided by 4 is 2. And 4 goes into 250 times, so 204 is one more 4 than that, so you go into that 51 times. So 51/2 would be our approximation for the area of this region. And that concludes the notes for AP Calculus on the topic of polar functions without the graphing calculator. Continue.